Okay, we want to talk now about nuclear reactions and...
Can you start again?
Sure.
Okay, go.
Right, we want to talk now about nuclear reactions, and they're different from radioactive decay, right, because radioactive decay are spontaneous. Right, well, in the case of nuclear reactions, sometimes they require an input of energy. Right, so broadly, all right, we're going to represent it with this expression. Right, so you've got nucleus A, right, that reacts with an incoming high energy particle, right, to give you another nucleus, right, with emission of a small particle B. Right, so there are two categories of reactions that we have. The first category is exothermic reactions. Right, these are reactions that give off energy. Right, and the next category of reactions are what we call endothermic reactions. Right, these are reactions that absorb energy. Right, so again, we're going to draw a comparison of the mass of the reactants and the mass of the products. In the case of exothermic reactions, right, the mass of the reactants, okay, is going to be greater than the mass of the products. The amount of energy that's given off, right, call it the reaction energy, E, right, is equals to delta M C squared, right, where delta M refers to the difference in the mass of the reactants and the mass of the products. In the case of an endothermic reaction, all right, now the mass of the reactants will be less than the mass of the products. The amount of energy that's required for this reaction, right, E equals to delta MC squared, right, where again delta M refers to the difference in the mass of products and the mass of the reactants. So looking at these two reactions, this energy, right, was given off often the form of kinetic energy of the products. This energy that's required is usually in the form of the kinetic energy of the reactants. Now it's important to note, right, that the minimum kinetic energy of the reactants for this reaction to take place has to be greater than E, right, which is this energy here. And the reason is this: if you have an incoming particle with a certain amount of kinetic energy, right, in order for momentum to be conserved, right, it cannot be that your products are at rest after this reaction. Okay. Now, there's another way of looking at reactions like this, right? That's in terms of the binding energies, right? And this is where it's important to be quite clear about the difference between an exothermic reaction and an endothermic reaction. Now, what if in the question you're not given information on the mass of the reactants or the mass of the products, but you're given instead information on the binding energies of your reactants and the binding energies of the products? Now, the way I think about it, right, is I think of a two-step process. So in order for this reaction to take place, the first thing that I need to do, right, is essentially to pull apart this nucleus and then form them again, right, to give us this nucleus. Pulling apart requires a breaking of bonds, right, that requires an input of energy, and forming this nucleus requires forming of bonds, and that's where energy is given off. Right. So if it were an exothermic reaction, right, if this were an exothermic reaction, then the amount of energy that's given off when the bonds are formed is going to be greater than the amount of energy that was required to break those bonds. So in such an instance, the binding energy of the products, right, be greater than the binding energy of the reactants. So the amount of energy that's given off in this case, right, is the difference between the binding energy of the products, the binding energy of the reactants. If it were an endothermic reaction, the binding energy of the reactants, right, be greater than the binding energy of the products. So the amount of energy that's required, right, in this case, right, is the difference between the binding energy of the reactants and the binding energy of the product.